Okay, so now we're going to use this integration technique of trigonometric substitution to find some other kinds of areas. So here's one we want to find, the area under the curve square root 9 minus x squared. So that's a semicircle radius 3. We see that circle here is blue. And we want the area from x equals negative 2 to 2. So we're basically cutting off the edges of this circle in a way that would be difficult to find with just geometric formulas. All right, so one way we can do it is with calculus. There might be some other clever way, but I don't know what it is. So we're going to start by saying that the area that we're looking for is equal to the integral from negative 2 to 2. I'm going to set it up just naively like that first. Square root of 9 minus x squared dx. And then I'm going to say, by the way, since this shape is symmetrical, I could cut it along its line of symmetry, just find this half of the shape and multiply that by 2 because the other side is the exact same. So I'm going to say that is 2 times the integral from 0 to 2 of square root 9 minus x squared dx. And we're going to see how putting the 0 here is going to make a huge difference in terms of evaluating the integral. All right, so we're going to do our substitution. So our standard substitution for square root of square root a squared minus x squared. All right, our substitution for that is x equals a sine t. All right, now our a is 3 because this is a squared right there. So we have a squared equals 3. So a squared equals 9. So a equals 3. All right, so that just tells us that our substitution is going to be x equals 3 sine t. And then we go and find out what the dx is. So dx equals 3 cosine t dt. Again, we're going to find changing the limits is going to greatly simplify the work, even though our first one is not going to be very nice. So if I start with the x equals 2 up here, right, x equals 2, so then what is t going to be when x equals 2? Because we're going to change this integral into terms of t. So then instead of x equals 3 sine t, I'm going to have 2 equals 3 sine t. So that means that sine t equals 2/3, and that means that t is equal to the inverse sine of 2/3. So this time we didn't get a very nice number for that upper limit, but that won't stop us from doing it. But it will lead us into some other interesting, important considerations. All right, so now when we have x equals 0, we just have 0 equals 3 sine of t. So that's going to happen when sine of t equals 0. So that just tells us t equals 0. So notice if we kept the lower limit as negative 2, we would be dealing with inverse sine of 2/3 and inverse sine of negative 2/3. This would be a lot more work. So now we just have inverse sine of 2/3 and 0. All right, so now we can say that the area in question is a equals the integral from, that's interesting, 0 to the inverse sine of 2/3 of square root of, so we're copying this integral down using these substitutions. So I'm going to have 9, and I'm going to have for x squared, I'm going to substitute 3 sine of t squared. So it's going to be 9 sine squared t. And then the rest of this becomes pretty standard. It's just a technique. But a lot of Calc 2 classes, that's what they're about. They're about technique. What are the different techniques you have for integrating things? If I integrate something like this, I do this trigonometric substitution. So I got to put in my dx, which is 3 cosine t dt, 3 cosine t dt. All right, and then I could just continue simplifying that. So my next thing, I've lost my 2. So that's going to equal 2 integral from 0 to inverse sine of 2/3. And then next step is we're going to pull out the square root of 9, which is 3. So we're going to pull out 3, and we're going to make this 1 minus sine squared t, this being the whole point of the trigonometric substitution. So we can change that. And, you can look ahead and say, this is just going to be cosine t. Pull all the 3's out. I'm going to add in some extra steps. I'm going to pull out the 3's. And then we have integral 0 to inverse sine of 2/3 of, we'll change this to cosine squared. So I have square root cosine squared t times cosine t. Don't lose your dt's. I'm losing my dt's all over the place. Yeah, so square root of cosine squared t is just cosine t. So now I can just really write that as 18 integral 0 to inverse sine of 2/3 of cosine squared t dt. So I think it's safe to say this integral is, when we start here, this integral is always going to come down to the integral of cosine squared, which is, again, why we learned that. So this equals 18 times, so we learned that cosine squared of t, the antiderivative of that is t over 2, plus sine of 2t over 4, evaluated from 0 to inverse sine of 2/3. All right, so that's what we have so far, and we'll start working on evaluating. Just a reminder, why is this integral this? Because we used a double angle substitution. That's how we got this result for this integral. So, keep those things in your back of your mind, where things come from. So you don't have to prove them every time, but know where that came from. It came from the double angle formula. All right, next we'll continue working on simplifying that.